Glad to see everybody here. This is actually my first time at the Ed Portal as well. So it's a very nice place, right? Although we didn't get any boat loco. So my name is Charlie. I am a fourth-year graduate student in the Department of Chemistry and Chemical Biology, just across the river. My research project focuses on the chemistry of alternative energy. So science and cooking, not necessarily related to what I do, but still probably much more interesting than my research I do in lab. And so I guess, oh, Tim, you should introduce yourself now.
Okay. Hi, everyone. My name's Tim. I am a fifth-year graduate student in the chemical biology program, and I work with E. coli, although I promise I'm not sharing that part of my science background with any of you tonight. But I've been working with the science and cooking team at Harvard and various projects they've been doing for like 3-4 years now, and it's been an immensely learning experience. So I hope that you all have a great time tonight. And I'll be talking a little more technically a bit later on in this presentation, but it's great to meet all of you.
Yeah, so again, thank you all so much for being here. I'm excited to tell you about science and cooking, how they mesh together, and how we're going to make ice cream later, and then aioli first, actually. So to kind of begin with, I'll tell you a little bit about the course Science and Cooking, right? It started off as a collaboration between Ferran Adria, shown on the right, world-class chef. Has anybody ever heard of Ferran Adria before? Yeah, a couple of you. What's the name of his restaurant? Do you remember? El Bulli. Very good. And do you remember what year it closed? 2011. And how many times was it voted #1 restaurant in the world? At least 6 by my count that I went through and checked on Wikipedia. So it started off as a collaboration between Ferran Adria and the School of Engineering and Applied Sciences as a charge from the Harvard curriculum in general education. And so they developed this class to kind of talk about molecular gastronomy. And Ferran Adria is known for basically developing molecular gastronomy, which is a deconstructionist view of cooking. He basically takes foods, breaks them down into their component pieces, and then rebuilds new and interesting foods from it. And so, this class has been wildly successful, and it has even had a run on the Harvard Extension School. It is now on edX and HarvardX, and now we're bringing it to you guys. So we're really excited to bring it out to a new platform. And so yeah, this is some of the food that Ferran Adria makes. He makes these crazy little raviolis with, I think it's clams and clam broth in there. You can see all the way through it. He makes these foams and jellies for desserts. And so one of the reasons that he wanted to build this class was to explain to everybody how he makes these things. And so one of the more interesting parts of the class on campus is that it actually has a public lecture series. Has anybody had the chance to go to any of those public lectures? Who'd you get to see?
It was actually a few years ago, and I went to some of them, and I don't remember.
Yeah. So they've had a lot of great chefs come through, including Jose Andres, who was actually a student of Ferran Adria a long time ago, holding all the oranges. Dave Arnold is a regular guest in the class. He has a cocktail bar and employs high scientific concepts to making crazy cocktails, as well as he developed this crazy flamethrower for grilling steak on a table. Our favorite pastry chef in Cambridge, Joanne Chang, is also a common lecturer for the class. And then the former pastry chef for the White House, Bill Yassi's in the bottom right, is also a guest in the class who's come before. So when you think about food, how do you like to describe it? What are some of the first ways that you guys would describe food? What about flavor, right? So what kind of flavors would you associate with some of these images, like the cake? How would you describe cake? Sweet, yeah. How about a pretzel? Salty, and then the steak? Savory, boom. Oh man, those are the 3 words that I picked when I got this, so I'm so glad you guys got the same ones. So we can also talk about the way things smell, the aroma, right? So coffee smells roasty, is how I would describe it. Lavender is going to smell floral and herbal. Cinnamon is going to be woody and spicy. And then the last thing that we can kind of talk about, just like sensorially, is the temperature, hot or cold, like steak on the grill or ice cream in a cone. And so we're getting there. Thank you very much. And for all of these, knowing what they're made of is hugely important for describing how they taste and how we know they interact with our tongues and our senses to be able to give us smell and taste. And so one of the other things that's important to know about the components of food is how food changes as we cook it, right? So these are all eggs shown here, and they were all cooked for the same period of time, but at different temperatures, right? So on the bottom right, what we have is a very low temperature, I'd say somewhere around 120 degrees Fahrenheit, all the way up to, on the top left, probably somewhere around 160 degrees Fahrenheit. So over that kind of a broad range, we can get drastically different temperatures, and these eggs are, technically cooked. And we know that it's a result of protein coagulation that causes these eggs to change shape. And in bread, right, we have flour and water and yeast that cause the dough to rise. As we bake the bread, we have the baking soda and baking powder then that can expand to make the bread rise as it bakes. And then also knowing the composition of the bread itself, when we toast it, we know what's happening to turn it brown. Does anybody know what these browning reactions are actually called? Maillard reactions. Very good. And do you know what the reaction is that's occurring? So they're called Maillard reactions, but do you happen to know what the molecules are? So the main chemicals that are involved in Maillard reactions are those of amino acids and those of carbohydrates or sugars as well to do the browning reactions that you see at high temperatures. And so what are some of the components of food? When you look at a nutritional label on the back of a bag of chips or on the back of a bag of cookies, what are some of the things that you see on there for nutritional content? Calories, good. So what about the nutritional part beyond calories? Like what is it made of? Protein, that is good. What else? Carbohydrates and fat, very good. So I got these in the wrong order this time, but we all kind of got there. So some of the fats that we think of, what are the common fats that you guys cook with? Saturated and unsaturated. Can you give me an example of one of each? Butter and olive oil. Yes. All right. Very good. How about carbohydrates? What are some of the carbohydrates you guys think of? Sugar, flour. Very good. Flour and sugar. All right. And then for protein, and we kind of saw it in a previous slide, one of the most common proteins that I think of is that of egg proteins. So, and chicken. Love chicken as well. So, we love all these ingredients. We love how they go into all of our food. But, to understand how we can manipulate these foods using science and measure them using science, we need to know what they're made of. And so you had mentioned earlier about saturated and unsaturated fats. And so if we look at a molecular level, that's what we get. So this right here is called a triglyceride. And in the dark gray are the carbon atoms, in white are hydrogen, and in red are oxygen atoms. And so this is an example of the way that I drew it in this program. It's more saturated than unsaturated. So this would be a better representative example of, say, butter. Carbohydrates, right? We said sugar and flour. So sugar is shown up here on the top. That's simple table sugar. That's called sucrose, and that's a combination of a glucose ring and a fructose ring. And then below that, we have an example of a starch, which is just polyglucose molecules. And then for the protein, we have ovalbumin. And this is what ovalbumin, the main protein in egg whites, this is what it looks like. Okay. And so today, though, at least for the first part of the activity, we're going to be focusing mostly on fats. And so fats, again, look like this. This is just a molecular drawing and then a molecular model of them. And one thing you'll notice is that there's a lot of carbon and a lot of hydrogen, not a lot of oxygen. So one concept that's important to know for cooking and just phases in general is that things that look like each other like to interact with each other. So fats like to stick with fats. Alternatively, there's water, right? That's also very, very common, and that's actually the fourth main ingredient that goes into all food. So water, as you can see, has a lot of red and a lot of white. And something special about water being made up of oxygen and hydrogen is that it can undergo hydrogen bonding. It's a special kind of bonding that it can do with itself so that it really likes to interact with itself. But as you can see, while there are a couple red dots in the fats, not very many. So fats and waters, they don't like to go together. What is one culinary example that you guys probably have in your fridges at home where you have fat and water together in the same place? Salad dressing, perfect. What kind of salad dressing do you like best? Greek? Anybody else? So I really like vinaigrette, right? And so this is an example of a vinaigrette that is settled out, where the emulsion, as we are going to call it, has totally broken and fallen apart. And so we have a layer of sediment on the bottom, a layer of vinegar in the middle, and then oil on top. And so when, the vinaigrette is one example of an emulsion when it's all mixed together and it looks more like this. And so an emulsion then is a dispersion of oil droplets in water. And they're formed just by simple agitation. Taking the salad dressing bottle, shaking it up really vigorously, you generally get an emulsion, but it falls apart once you put it back into the fridge, right? What's one example of an emulsion that you think that is more stable than vinaigrette? It doesn't fall apart. Mayonnaise. Very good. So that's actually what we're making today, is we're making a very simple mayonnaise. And so mayonnaise is a suspension of fat droplets in water that is stabilized by using something called a surfactant. And a surfactant looks like this. It has a head group and a tail group, where the tail really looks like the oil molecules and likes to interact with them, and so it can sit in the oil. But it also has these head groups that really like to interact with water. And so that way, these surfactants can actually sit at the surface, stabilize the oil droplets, and keep the whole thing from falling apart. And I know I said we'd get to texture, but I actually don't have that till after we do the lab, excuse me. So we'll talk about that in a little bit. But for now, we're going to get started on doing the lab. And so on your tables, you have all the ingredients you need, plus you have some not extra, but you also have your lab reports and lab procedures there. And so we have, I believe, 2 mortar and pestle per table. So that means we're going to be able to make 2 aioli, but we're going to be doing it 3 times over, essentially. So what we're going to do is we're going to break up some garlic and macerate it in the mortar and pestle. And then we're going to start adding oil to make our emulsion. And that's actually the simplest form of aioli, called aioli. And then we're going to add mustard to it, if you like mustard, and see how much more aioli we can have. And so within garlic and within mustard, there are small molecules that are actually surfactants. But then eventually we're going to add egg yolk, if you'd like, and then make even more of our emulsion. And you'll find out later why egg yolk is such a good emulsifier. So why don't you guys go ahead and stand up or get into position, and we'll get started on the lab by cutting up your garlic and chopping it into little bits and smashing it up in your mortar and pestle. And there will be people floating around to kind of help you guys as well. Test. Is this on? Yes, it is. Okay, so who ended up with an aioli that looked like this? Impressive. It's very hard to do, as I'm sure you've learned. Lots and lots of exercise is needed to get the arm strength to be able to do that. Oh, there's a good one over there. That was good. Do you want to hold yours up over here? Yeah, get the big scoop. Yeah, look at that. Very well done. That's excellent. So we have the bread and the carrots on the table for you guys to enjoy. And I'm going to give you a little bit more of the science here about how this works. So again, this is an emulsion. And an emulsion, again, is the two-phase system where we have 2 liquids suspended within each other. In this case, we had droplets of oil, olive oil, suspended in water. And so where did we get the water from in our example? Garlic, mustard, and the egg yolk. Very good. Yeah, so there's a little bit of water in all those, although the most obviously in the egg yolk. And so the water then becomes our continuous phase. and the oil becomes our suspended phase. And if it is not stabilized, you can actually have complete emulsion failure, coalescence, and separation into two phases. So if you watch this GIF backward, that's basically what the failure would look like. Everything just rises up to the top. So again, we use a stabilizer in the form of garlic and the mustard and the egg yolks. Garlic, as I'm sure you saw, was not the best emulsifier. You really had to get it down to a super fine paste. The salt that you added to the garlic actually helped draw water out of the garlic so that you could make an emulsion to begin with. The mustard was a little bit better, but still not great. Mustard is actually more common for making a vinaigrette when you have a lot of continuous phase and about an equal amount of your dispersed phase, which in this case is the oil. And so the egg yolk is actually the best emulsifier. You guys, I'm sure, saw that you were able to make the most aioli utilizing the egg yolk, and that's because the egg yolk surfactant looks like this. It has these tails and these head groups that are really, really good at stabilizing the interface between the oil and the water. If you remember earlier, that the oil has a lot of these tail groups, lots of carbons, lots of hydrogens, and the water is a lot of oxygen and a little bit of hydrogen, but they don't like to interact. Like dissolves like is a term that we use often in the chemistry lab, and it very much holds true here. And so we actually use, in the egg yolk is a surfactant called lecithin. The main component of lecithin is something called phosphatidylcholine, and that's what this molecule is here. And this is just a 3D model and the drawing of it. And so if you look, again, the surfactant has the tails, and if you remember the depiction of the triglyceride, it has the same tails, right? Really long carbon chains with lots of hydrogens. So that's what's interacting together. And then the head group here, it actually has two charges. It has a phosphate group with a negative charge and a nitrogen with a positive charge. And that's a special kind of ion called a Zwitter ion. They're actually pretty common in biology as well. And so this is kind of just a 3D model of what this interface looks like. And I know it's a little jumbled up to see, but we have like a big fat triglyceride here, and then we have a phosphatidylcholine here, so you can see these leg groups interacting all together. And then over here we have our two charge groups and water. So we all know that salt dissolves very readily into water, and so it's those same interactions that help salt dissolve in water that allows these head groups to stabilize the junction between the two phases. And so I mentioned texture earlier. We mentioned texture earlier as a way to describe food, so now I'm finally getting to it. One of the things that we can talk about with texture is how soft or firm it is, if it's crunchy or smooth, right? For liquid foods, what we have is viscosity. How thick is our liquid food? And so for something to be a liquid, what has to happen? It has to be able to pour, right? That's what we would call a liquid. And so what that is, in the case of, say, our emulsions that we're trying to make, like the example of a vinaigrette, that's definitely a liquid. We have small droplets, but very, very few of them in our continuous phase. And so these small droplets can easily move past each other. Look at all this blue space they have to move around. And so because they have so much space to move around, they can just pour out and flow anywhere that they are poured into a container. And so with viscosity, the way that we can measure it is by measuring the amount of dispersed phase, oil, in the total volume of our emulsion. And so as we increase the concentration of our dispersed phase, what's going to happen, do you guys think? It's going to thicken. Very good. Right. So if we add in more oil droplets, we see that obviously they're getting in each other's way. If we were to try and pour a solution that looks like this, it wouldn't move super quickly. It would pour something closer to that of like maple syrup, perhaps, instead of water. And then as we keep adding oil, and this is actually the phenomena that we started to observe today, is that these droplets, because they're stabilized by the surfactants, they actually start to pack in very tightly together. there's very little space for them to exist, and so the shapes of the spheres actually start to deform. They're in constant contact with each other. And so how do you think that affects the viscosity? It totally stops it. So the viscosity completely goes away, and we actually end up with something that's more of a solid. And so I was walking around and encouraging you guys to keep adding oil to some of your emulsions, because the more oil you add, the more droplets you're going to make, the more compression of your droplets that you can handle because of our surfactant, and therefore we can actually end up making a solid. And the way that we can measure texture in solids is through something called elasticity. Elastic behavior is the tendency of a material to be deformed in some fashion and then rebound to its original state. And so that is something that is perfectly elastic. And we can describe it going from a liquid to an elastic solid. We can describe it based on the volume fraction of oil that we have in the water. And so at some point, we're going to hit something called the critical volume fraction, which I've delineated down here as 0.64. So that's the amount of oil in the total solution that would then ultimately give us a solid. So at some point, if we end up with, say, 80% oil in our emulsion, knowing certain other factors about the bubbles of oil in solution, we can actually measure the elasticity, how well this material would rebound when compressed. And so ultimately, if you add enough oil, we should end up with a nice solid like this. And this is Nandu Chubani. And he made this aioli. We actually have a video of him making it. It took him like 5 minutes. It was incredible. He had this huge marble pestle, mortar, and then a nice little wooden pestle, and that you can see here. And he just knocked it out like that. It was really incredible. And so some of you actually were unfortunately unable to get a solid emulsion, and that is okay. And so one way that I was trying to kind of help alleviate that fact is by utilizing something called xanthan gum. And so xanthan gum is a polymer molecule which looks a lot like the starches that we had mentioned earlier, right? So xanthan gum looks something like this. And it is a fermentation product from a bacterium called Xanthobacter, which is then they take that polymer that it makes, pulverize it, and then sell it in this packaging. And so if you buy a tub of mayonnaise from the store, it's definitely going to have xanthan gum. And it actually helps to stabilize the emulsion for extremely long periods of time. And you actually only need something like 2% by weight to make a stable emulsion utilizing xanthan gum. And so with that, I'm actually going to hand the stage over to Tim, and we are going to get started on ice cream. I agree.